Hello everyone, this is the class of ECE350, the principles of automatic control. Welcome back to the online way because we are in the big snow today, so we have to stay at home and our class will be online again. Okay, let's just sit at the home and can have a class right now. Today we will keep working on the structures. Okay, this is the ECE350, the class. This is the fourth week, Wednesday. We want from a structure to a transfer function. All right. We want to find the transfer function if we have the structure. We study example like this. Alright. Okay. Alright, look like this. And we have some functions. I just put like this is a h1, h2, h3, h4. Okay, and g1, g2, g3, g4. Which one? G4. This g4. Okay, and those bar without any letter, that means just 1. Times 1, you think. Okay, and the input side is x of t and y of t, the output. We want to find the transfer function, find the y of s over x of s, the transfer function. Now how to do it? We can list some equations. We go over the graph, all the details, write some equations, but usually that costs a lot of time. And we can work in another way. We try to merge some parts together, right? To erase some paths and merge it to some other place, then make the graph simpler. And then finally we can have the whole transfer function, kind of reduce the graph. But this one we cannot do it directly. You can see we have 3 basic pieces, right? Basic structure, the parallel connection, right? Parallel connection, the cascade connection, right? 2 parts connect together, or a feedback connection, right? A feedback connection. But you look at here, it seems we do not have simply like this. They all merge together. So we can do some, before we start use these 3 to simplify the graph, we need to do something. We can separate some part. Actually here, you see, this point, the signal go in these 2 ways. So we can separate this part, like here, like you see, this is a part, this is a part. These 2 parts share this path, right? If we separate them, then we can make it we will have something looks like this. And here's a similar thing. This part, you see, this is separate. This here and here, we also share some part. So we try to separate. Actually, we can separate it like this. Here's G1, I keep it, and G4, I also keep it. Okay, this part H2. Now I use 2 H2. This is also H2. This is also H2. Okay, it works like this. You see, you can imagine the signal go to here. Here's a separate going down. Then you have H2. Then go to here. Then separate. Okay, now I go here. This is G2. H2 G2. H2 G2. And the other side is H2 go to here. H3, right? The same thing, right? And okay, these two we can combine together. H4 and the G3, they are connected as a cascade way. So this is just times G3 and H4. I can times them together. Alright, here we separate them. Okay, then this place is up and down, so I can still separate like this. Here's another H2. Here's 1. Then H4 is combined with G3. Okay, I separate it in this way. After this, now it is somehow simple, right? Like this part, this is a parallel connection, right? This is a parallel connection. This is a parallel connection, right? This way and this way. So I can put these two together. And this one from here until here, from here to here, this is a two-part, right? They are cascade connection, so I can combine these together. And then this path, this is go backward, right? This is also go backward. So these two, actually these two combined together is a parallel connection. So I can merge these two together. Okay, now we can have like this. G1 is still G1. Okay, here it is G4. Now it's G4 and plus this, right? H2 G3. H2 H3 is a cascade connection. I can merge these two together and add these parallelly. So it is G4 plus H2 H3, right? This part now is here, and this one and this one. Okay, now is here's a H1, and here this path I have G2 H2, and this path I have H2 G3 H4. Alright. Okay, then these two can combine together and times H1. So this one now looks like, yeah, I can just write this way. Here's a G4 plus H2 H3, and here's a feedback. This feedback is H1 times G2 H2 plus H2 G3 H4, and here's a G1. Alright, now we can have the whole transfer function. I write it here. Y over x equal to, here's the feedback part, so it is a G1 over 1 minus the feedback loop. Feedback path is a H1 times G2 H2 plus H2 G3 H4. Right. So this is a, yeah, like this, and times this one times G4 plus H2 H3, right? Here's a like a cascade connection, right? So like this. Okay, and then let me do some simplify. So y over x equal to, here's a G1 times G4 plus H2 H3, right? This one times this one, and denominator is 1 minus H1 times G2 H2 plus H2 G3 H4. Okay, now we can have our final answer. Alright, so we can work like this. Now when you have some graph, it looks complex and some part is hard to separate as like some kind of a feedback or parallel or cascade way, then you try to separate some part. After you separate them, then you can find some structure looks like this way, then you can merge them and finally make the whole structure become simpler and simpler, and then you get your final transfer function. You can always work like this. However, this is still a complex process, right? Here, this structure, right? we do 1, 2, 3 times, and merge some parts, separate and merge, and totally 3 parts. If you have a structure even complex than this, maybe you need to do a lot of work to find this final answer. Okay, so today we will consider a new method. We use a formula to do this. So this is the gain formula. Gain formula to find transfer function. Of a structure. Okay, what is the gain formula? Gain formula, it is just like this: y over x equal to summation some I run from 1 to some k. Here's mi delta I over delta. It is just like this. This is the formula. Okay, now let me explain the details. First one is this k. Here's a summation, right? That means you have several terms in the numerator. Now what is the numerator? How many terms do we have? These terms k equal to the number of forward path from x to y. Straightforward path from x to y. Now you have a graph. You have a input part. You have an output part. From input to output, how many paths do we have? We can check like in this graph. X to y. How many forward paths from x to y? You see, the top line it is, right? Go straight ahead. This is 1. And another is here. You see, to here, then going down, then left, and the right, then up and the right again. Okay, so this is also a path, right? This is also a path. Start from x and finally reach y. Do we have any more? Like here, we can go this way. Oh no, we go back. The path is straightforward. That means you never go back to the same point, right? Like this, you go back to the same point. No, this is not go directly to y, right? You will repeat some part. So we just strictly from x to y. So we have two paths. These 2 paths will give us 2 terms in the numerator. And actually this is correct, right? You see this graph with this transfer function, how many terms in the numerator? It is a g1 g4 plus g1 h2 h3. You see, g1 g4, this is this path, and the g1 h2 h3, you see, g1 h2 h3, the second path. So in the numerator it's just these 2 paths. Okay, this is the what is k, and then what is mi? This is the gain of the i's forward path. Yeah, you have a path, then you have a gain. Like here, the first forward path from x to y, the gain is just g1 times g4. Okay, g1 times g4. So this is just mi. And I will run from 1 until k. So how many paths? Then you will have how many mi's. And then delta I. Okay, before we know delta I, we need to know what is delta. Delta is in denominator. Delta is 1 minus summation of some terms. I say Li and plus some terms. I will explain what are these L. Some terms Li times Lj, and then minus more terms Li, Lj, Lk. Okay, So what are Li? Li, the ith loop gain. The ith loop gain. Make sense? Loop. So you look at here, we have loop here in this graph. You see, this one go forward and turn down, then backward and coming up. So this is a loop, right? This is a loop. And we can have similar thing. If you have some place and turn around, you can follow this, turn around forever. That means you have a loop. Okay, here's the same thing, right? G1, another one, G1, H2, then go ahead to here, then H4, G3, coming up. You see, this is also a loop. Here, right? This is also a loop. This is also a loop. So this is a loop. This is a loop. Then for you need to minus the gain of the loop gain, minus. Here summation means all of it. Yeah, summation. How many loops can we have? Okay, here you see, like in this graph, we can have these two loops, right? Do we have more? Here's a, okay, so go back. Here's a separate, right? So if you go this path, then we have to go to the end. No loop, right? We go separate going down here. Then here you have two choices. If we go left, then this is the only loop, right? Down and left, no more choice. Here you have to follow the path, follow the arrow. So this is one loop. And go this way. If you're coming up, then you go back, go outside, right? If you go down, then the right, then up, then you will go to Y. No loop. If going down and right, okay, going down again, then backward to here, then coming up, this is the only way, right? Coming up, here's not, this is the only way, right? This is the only way. Coming up, okay, here is just, you have a loop, right? So this one you have another loop. So you have two loops. And you see, denominator is 1 minus first loop minus second loop. Get it? You see, first loop is H1, G1, H2. H1, G2, I think I lost something. Oh, here, sorry. Here I lost here I lost the G1 here. This is a feedback, right? Here's a G1. I lost the G1 here. That's a G1 here. Then here I also need a G1. And then the first term, it is just that loop. You see, H1, G2, H2, G1. So H1, G2, H2, G1. Right? Yeah, G1, G2, H1, H2. This four. This is this small loop. Right? And second term, H1, H2, H4, and G1, G3. G1, G3. And H1, H2, H4, right? So this is this large loop. So this denominator, it is just 1 minus first loop minus second loop, as in the formula. Denominator is 1 minus first loop, second loop, if you have, then third loop, fourth loop, all the loops, minus all the loops. Okay, then here you consider here this one, you need a plus multiplication of two loops. Okay, but we have a condition. Here. Li, Lj, they have no common part. They do not touch. They do not have. They do not share any path or point. Okay, no common part. And this 3 is also similar. Lk. So all the rest part, when you consider times multiplication of 2 loops or 3 loops, you have the requirement. They cannot be any way to connect to share any part, to share a point or share a path. Okay, then you look at this graph. You see these two loops? We have two loops here in this graph, but they share this part, right? H1, G1, H2. Both loops contain H1, G1, H2. So these two loops, they share some part. Then we cannot use the multiplication of these two. Okay, so no more, right? In the denominator, we have no more terms. Just 1 minus all those loops, and no pair of loops, they do not touch each other. No triple loops, 3 loops as a pair, as a group, they do not have any common part each other. So in this example, the result is it is just delta is 1 minus all these loops. Just minus loops, no this part, no this part. Alright. And then after we have dirt, now we know what is dirt I. Dirt I equal to same as in dirt, but only use the loops that has no common part with the ice path. Alright. Yeah. So delta I is also 1 minus some loop and plus pair of loops and minus some other 3 loops times together, in case when we have pair or triple or more, these loops, they cannot touch each other. Okay. Yeah. And now delta I, we do the same thing, but we only use those loops do not have any common part with the ice path. Now look at this graph, this structure. Totally we have 2 loops, and the first forward pass is here. You see we have common part with both loops. So for delta 1, no loop can be applied. That means we only have this one term, right? There's no rest part, no other loops, no loops, just the 1. So delta 1 is just 1 in this graph. And the second pass is here. Right? Second forward pass from X to Y is here. And okay, it still has some part shared with the other with those 2 loops. So for second pass, that delta I is still 1 minus nothing. It is still just 1. Alright, now we can see this one. We can have the structure. Example 1. Okay, this is example 1. Example 1 continuously by gain formula. The number of forward paths 2 is 2, right? K equal to 2. The path looks like this, and right, we have 2 paths. One is this, one is this, and loops. We have 2 loops. One is this, one is this one. So we have L1 equal to the small loop. Small loop is just it is G1, G2, and H1, H2. Right? A small loop. And the larger loop, L2, this is L2, this is L1. L2 is G1, G3, and H1, H2, H4. H1, H2, H4 is a large loop. And here these two paths, this M1, the first pass M1. M1 is just go ahead, this go forward, right, straight ahead. This is G1 times G4. And M2 here, we have a turn around here, right? So we have G1, then H2 and H3. And now the delta 1, it is just 1. And delta 2, okay, I write equal. And the delta 2 is also just equal to 1. Because L1, L2 touch M1. M1 is the first forward pass. And here is L1, L2, both L1, L2 touch M2, right? So, sorry, this is 1. Delta 2 is 1, not delta 2, okay? So both is minus 0. This is minus 0 actually, right? Minus 0, it is just 1. Alright, now we have the transfer function. Y over X equal to the forward pass, first forward pass, G1, G4 times delta 1 is 1, right? Times delta 1, so it is just G1 times G4. And the second pass is G1, H2, H3 times delta 2 is also 1. And denominator is dirt, so it is 1 minus, we have two loops, so minus G1, G2, H1, H2, this is a loop, and another loop minus G1, G3, H1, H2, H4. Then you are consider, do we have like two pairs? They do not have common part. No, we only have these two loops, and they have common part. Right? Both contain G1, H1, H4. So no more terms in the denominator. And the final answer is just this. It is just this. And we know it is as same as this one, right? As same as this result. As same as this result we obtained in early time, right? Is this one? Are they same? G1, G4, G1 times H2, H3, and 1 minus H1, H2, G1, G2, right? This first term. Again, second is H1, H2, H4, and G1, G3. H1, H2, H4, and G1, G3. Right? So they are same. They are same. Alright. But by this method, you do not need separate them, then combine them like this. You can just look at this graph, investigate on the graph directly, and you can have the structure. So this is the gain formula. And of course we have some requirement. Not always we can always use the gain formula, but we need some requirement. What is that? Here X and Y. So this point is an input point. This is output point. Make sense? This is like a source. The signal coming out from here, right? All the other point, they are not input point. Like here, this point, it is not input because some signal from somewhere else coming to it. So this is not the input, right? This is also not input. So the input xt is the only point in this graph. Xt is the only point with the input to be an input. This is output. You can use any one as output, but the input must be this one. Right? Any others you can use it as a output. Right? Yes. now we have this one as output. So you want to find, if you want to find the transfer function from any output related with the input, you can work like this. Like for example, I have a point here. I say this is a W of t. W of t. Can we find the transfer function from x to w? Yes, we can do the similar thing. Example 1, continue. Find w s over x of s. The graph is still here. Right? Graph is still here. We want to find w over x. Then what it is? We do the same thing. The forward path how many forward paths do we have? This way. Okay, now just one path, right? Just this. Go to here. So it's from x to w. We only have one forward path. Only one. And m1. That is g1, h2, h4. This is forward path. And the loops, same with early work, right? Early work. Yeah, we already have two loops. Then okay, then we can have the transfer function. ws over x of s equal to the numerator. It is just g1, h3, h4. And the two loops, all these two loops, they have common part with this path, right? So no delta 1. Delta 1 is just 1. Yeah, times delta 1 equal to 1. And denominator actually is the same as previous cases, as the y cases, right? Now it's a w. It is 1 minus the loop. The small loop is g1, g2, h1, h2, and minus the other loop, the large loop. I have g1, g2, g3, and no g3, sorry, no g1 and g3, and h1, h2, h4. Okay, so this is a w over x. Yeah, you can pick any other point at the output point. You can get a similar thing. But then more. Now find find y over w. Can we? ys over ws. This is also kind of transfer function, right? But now w is not the input. So for this one, y over w, we need to use gain formula only if the denominator is coming from an input point. This is not input, no input, but we know x is the input, right? In the graph, only x is the input. So we can have y s over x of s, right? We can find these by gain formula. Actually, we already have it, right? Over ws over xs. We can write it in this way. Then each part we can use the gain formula, and then combine together. It is just this one. Okay, now we have it. Y over x. We have y over x, right? It is just this one, right? Okay, and w over x is this one, and this one over this one, right? This one over this one, and you know they have same denominator. So the denominators will be cancelled. We only have numerator and this numerator. And which will be on the top? This will be top, right? This will be bottom. So y the numerator is G1. I just copy this one. Okay, G1 times G4 plus H2 H3. Okay, I copied it. This is the numerator of the y over x, and the numerator of w over x is here. So this is just G1 H3 H4. All right, so we have y over w. We have y over w. All right. This is the case if you want to pick two signals. Both of them, they are not exactly the input, but you still want consider, like here you consider w related with y. You think w is a kind of input related with y, or the signal in the y is the output, and this output is coming from somewhere and w. Now of course this signal is coming from the input side. W is not really the input, but it's still some signal is coming from w to y, right? So we can also consider the transfer function between y to w. Then we can work like this. We use the input. We use that input for each y and the w, and then combine them together. So we can work like this. All right. Okay. Now we can see more examples. One more example. Example 2. We have here I only use the signal flow graph. If you have a block diagram, actually you can apply the formula in the same way. All right. I have this one. I have like this one. This one. Okay, like this, going down. Here's going forward, and okay, like this. And I have H1, H2, H3, and G1, G2, G3, like this. Okay, and here's a input X. Here's the output y, and I select any one, like which one is, like this one is a w. We want to find y over x. We want to find if you want, you can also just write as y over x, like a w over x, actually in S domain, right? Transfer function, or y over w. We want to find these three. Yeah, here x is the input, right? You see, this is the signal coming out from here. So this is the input, the only input, and this one is the output. This one must be output. Must be output. It is meaningless like to consider like a w over y. Yeah, you can still formulate. You turn around this result, you get a w over y, but you know the signal will not go back from y to w in this system. Yeah. Okay. Anyway, let's do these three. The first one, from y to x, the forward path. Let's see. The straight ahead. This is the first one, right? And the second one is here, right? Going down and okay to there. Do I have third one? Yeah, this go ahead to here. The guy coming down and the left and then the right, down and the right and up and again. Any more? Go straight ahead. If I separate, if I turn around here, then this is the only way, right? Oh, we can do this 2 times. Yeah, okay. So the path will be, this is 1, this is 1, this is 1, and this is 1. So we have 4 paths. 4 passes here. And we have M1 equal to H1, H2, H3, and M2 equal to here's G1, right? G1, H2, H3, and this pass is M3, which is H1, H2, then G3, right? And this one M4, it is G1, H2, G3. Alright, so we have 4 forward pass, and the loops. How many loops do we have? Do we have loop? Loop will be something go backward, right? This one is not. This one is, okay, here's a loop, right? Here's a loop. Do we have any more? Is this a loop? No. Is it a loop? No. Can we have some larger loop? Well, if you're going down here, then this is the only choice, right? Going down here, then you have to turn left, and then coming up, then backward. So this is the only loop. This is only loop. Here's no loop. They go, well, this is a, yeah, no loop. So oh, we only have one loop. Okay, in this graph, loop just only one, L1. This is H2, G2, the only loop, one loop. We only have one loop. Now the transfer function, y over x equal to, denominator will be 1 minus the loop, and plus 2 loops. Okay, we do not have, we only have one loop, so that's it, just 1 minus this loop. This is the denominator. The numerator, you will add these 4 together, and each one you need times delta 1, delta 2, delta 3, and delta 4. And okay, you see this L1, this is the loop. This is loop. Loop is located here. Right? Loop is located here, this way. Right? Loop is located here. So, you know, all these 4 forward paths, they have common part with this loop. Okay, so that means delta 1 is 1, delta 2 is 1, delta 3 is 1. All of these delta 1, 2, 3, 4, they are 1s. Okay, now we have, this is just M1 plus M2, M3, and 4. So add the 4 together. It is H1, H2, H3 plus G1, H2, H3 plus H1, H2, G3 plus G1, H2, G3. Okay, that's it. This is y over x, y over x. And then we can check w over x, w over x. W over x, how many forward paths do we have? We have 2, right? We have 2. Why is this? Just here. And this one is another one, right? Do we have 2? Any more? No more. Okay, so we have 2. This is M1 equal to just H1, and M2 equal to G1. And then the loop, well, still the both paths, right? The loop is here, loop is here, loop is here, right? So you see, you have common paths. Here you have a common point. So no loop will be applied. So this delta 1 is 1, and the delta 2 is also 1. And the delta is the same. Delta is the same. So we have w over x will equal to a fraction. The numerator is m1 times delta 1, that is just h1, and m2 times delta 2, it is g1, and the denominator will be same as here, is 1 minus the loop, 1 minus the loop, h2 g2. Okay, so this is a W over X. And then we want to have Y over W. We just Y over W, right? Y. They have same denominator, so just use the numerator. Y has a numerator here. This one, H1, H2, H3 plus G1, H2, H3 plus H1, H2, G3 plus G1, H2, G3. This is the numerator of Y. And the numerator of this Y, W over X is H1 plus G1. Alright, this is we have our answer. We have our answer. Okay. We can try more example. We have 5 more minutes, 4 minutes. I can just give a group, give you a graph, and then we can try to find how many loops and forward paths do we have. Okay. Example 3. Okay. Like these. I have this one, I have this one, I have this one, and I have this one, I have this one, and okay, yeah, like this. I give some letter here. This is a G1, G2, G3, and this is a H1, H2. This is a negative H3, negative H4, and H5. Alright. Then forward path. Forward path, of course, you know from where to where. Here's from X to Y. We want to find Y over X. So start from X to Y. The forward path, okay, this is 1, and okay, see here are coming up, right? Another one, and here's coming up another one. So I have 1, 2, 3. I have 3. This one, and this one. I have 3 forward paths. Okay. And 1 equal to straight ahead is a G1, G2, G3, right? And M2 is this small circle, so G1, H2, G3, G1, H2, G3, and the top pass, highest pass, this is is M3. Here's M3 is H1 and G3, H1 and G3, right? And then loops. Okay, where are the loops? Here's a loop, here's a loop, right? And here's another loop. Any more? Okay, because this path, actually we have like this path, right? So use this path and this one and this one. We have some other loops. Oh, this one give us a lot of loops. I have see. You see, loops. This is one loop. This is one loop. This is one loop. I have 3 loops here, and then I use this path. Right. This is one loop, and this is one loop. 2 loops, not here. Right. This is one loop. Like this one is loop, and this one is also loop. And then I use this path H1. H1. Okay, this is also a loop, right? The largest, the totally outside. This is also a loop. Any more? Okay, I have 1, 2, 3, 4, 5, 6 loops, or 6 loops, and 3 paths. Now what will be the transfer function? Okay, I leave it here. If you are interested, you can try to write it out. It is not complex, but it's long, right? It's long. Yeah. Yes, you have 6 loops, and you need to consider, can you pick like 2 loops they do not have common part? If you can find that kind of things, then you have more terms in the denominator. And also you will consider whether any loops do not have common part with the forward path. If you can find, then you need to make some change. Oh, I think we do not have that. Okay, it's fine, not so complex. You can try to write it. Yeah, denominator just 1 minus all these loops, and the numerator just add them together. Yeah, okay. Alright, that's all for today. See you next time. Hopefully we can go back to campus on Friday, right? Alright, bye bye.